Let's start chapter number 14, General Properties of Waves. Feature of waves. Waves transfers energy, not matter. Waves carry energy without carrying matter along with them. This is a general diagram of wave. The upper side is called as crest and the lower side is called as trough. This is the distance of amplitude and this is the distance from one point to another is called as wavelength. In sound waves, air particles vibrate back and forth but do not travel with the wave. In water waves, floating objects move up and down but stays in the same place. This shows that the wave transfers energy while the particle only oscillate around fixed position. This diagram shows the vibration of an individual air molecule. Oscillation means repeated motion around a central point. Examples: ripples, water particles move up and down. Sound, air particles move side by side. This vertical direction is called as oscillation direction. This horizontal direction is called as propagation direction. These are the longitudinal waves and these are the transfer waves. Here there is one worked example. A toy duck floating on water moves up and down as waves pass underneath but does not move along the surface. This demonstrates that water waves transfer energy but do not carry matter with them. Each position vibrates in place rather than traveling with the wave. Wave in ropes, springs, and water. When waves move through a rope or a spring, the material vibrates but does not move along the rope. In the sea, objects bob up and down, showing the water is not traveling forward. A ripple tank is used to observe wave motion clearly from above. Describing waves. The key terms. To accurately describe wave, these key terms are needed. Number 1, wave front. A wave front is seen from above as a line joining points that are in the same part of the wave cycle. The spacing between wave front represents the wavelength. Closer spacing, shorter wavelength; wider spacing, longer wavelength. Amplitude, the symbol is A, capital A. The maximum displacement from the undisturbed rest position. It is measured in meters, found by measuring from one center line to the peak or to the trough. Then we have wavelength, its symbol is lambda. The distance between identical point of two neighboring waves. For transfer waves, peak to peak. For longitudinal wave, compression to compression. It is measured in meters. Then we have frequency F, the number of waves passing a fixed point every second, measured in hertz, Hz. Now, let's talk about crests and troughs. A crest means peak in the highest point above the rest position. A trough is the lowest point below the rest position. Wave speed, the speed at which energy in a wave travels through the medium. Wave moves a certain distance per second. Worked example for amplitude and wavelength. Amplitude is shown by the arrow from rest position to the top or bottom of a wave. Wavelength is shown by an arrow between two identical points on successive wave. The wave equation, the equation linking wave speed, frequency and wavelength is V is equals to F times lambda. V is the wave speed which can be measured in meter per second. F is frequency, its unit is hertz, Hz, and lambda is the wavelength, its unit is in meters. Applies to both transverse and longitudinal wave. Frequency and period. Time period is t, time taken from one complete wave. Relationship is f equals to 1 over t and t equals to 1 over f. Period measured in second, which is s. Worked example, suppose time is 2 seconds, f is 1 over 2, which is 0.5 hertz, and v is 0.15 meter per second. So if we need to calculate lambda, we'll divide v over f and we will get our wavelength in meters. Types of waves. Transfer waves. Vibration are at right angles to the wave direction. Example, electromagnetic wave, light waves, radio waves, X-rays. Ripples on water and seismic S wave. Now let's talk about longitudinal wave. Vibrations are parallel to the wave direction. Example, sound waves, seismic P waves, waves in stretch spring. They require particles, so cannot travel in a vacuum. Compression is equals to particle close together. Rarefaction means particles spread out. We have a comparison table which shows the property and then whether it is present in transverse wave or a longitudinal wave. So vibration direction is perpendicular in transverse wave and it is parallel in longitudinal wave. Structure, peaks and troughs are there in transverse wave, whereas compressions and rarefactions are there in longitudinal wave. Travels in a vacuum. Transverse wave, yes, electromagnetic waves only, while longitudinal wave do not travel in vacuum. Medium, transverse wave has solid and liquid surfaces, while longitudinal wave has solid, liquid and gases. Pressure and density in transfer wave it is constant, whereas in longitudinal wave it is changing. Wave behavior. All waves can show reflection, refraction and diffraction. Reflection, a wave bounces off a surface and stays in the same medium. Angles measured from the normal, a perpendicular line. Refraction, a wave changes speed when it enters a different medium. This causes a change in wavelength and direction. Frequency stays the same. Slowing down, bends towards normal, wavelength decreases. Speeding up, bends away from the normal, wavelength increases. Now let's talk about diffraction. When a wave passes through a gap or around an obstacle, it spreads out. Diffraction is strongest when the gap size is similar to the wavelength. Longer wavelength spreads out more. Ripple tank investigation. Used to study reflection, refraction, and diffraction of water waves. These ripple tank diagram, it's measuring waves in a ripple tank. Wave pattern are projected below the tank for viewing. Reflection. A barrier placed in the water causes wave fronts to reflect. Law of reflection applies. Angle in is equals to angle out. Refraction. A glass block under part of the tank creates shallow water. Waves slow down in shallow region. Wave fronts gets closer together and the direction changes. Diffraction. Barrier with a gap show wave spreading after passing trough. Effect depends on wavelength compared to the gap. Changing vibration frequency changes wavelength. High frequency, short wavelength, less diffraction. Low frequency, long wavelength and more diffraction. With this we have finished our chapter. See you in our next chapter.